All right, let's continue our discussion of conservation of matter now. We're going to introduce the concept of the mole. Now, the mole is a pretty foundational idea in chemistry. It's something that we use pretty much every single day in the chemistry classroom. So, as a foundation to this, just kind of as a core, you have to understand that atoms are small. I know it's not a startling revelation to you, but atoms are very small. So a lot of them must be present in the samples that we use in a regular scale or a large scale, if you think about it in terms of the size of the atom. So because these atoms are so small, what we have to do is we have to consider we need to have some kind of a number that represents a lot of these particles. In order for it to make sense in a large scale, we have to have some number that we can relate to. Along these lines, let me tell you this. It's like another representative number. If you're talking about eggs, you would say that 12 eggs is equal to 1 dozen eggs. Okay, so this word dozen means 12. So 12 eggs is 1 dozen eggs. So the breakdown is you have the quantity, you have the representative number or the unit, and you have the substance is your egg here. Now the number of atoms that you find in 12 grams of pure carbon-12 is, this is a standard that we use to define the number of particles that we refer to as a mole of a substance. Okay, so we're using, here's our sample of carbon-12. We put that sample on a scale and we determine that that has a mass of exactly 12 grams. And what we do is we want to know exactly how many atoms of carbon are in this. So the number of those atoms that we find in this mass, that is our standard used to find 1 mole. Now we have a name for this number. It is Avogadro's number, named after Avogadro, famous mathematician, scientist. I believe he was an attorney as well. But essentially, he did some studies with gases, and that led him to receiving the honor of having this number named after him. Now, the number 1 mole is equivalent to 6.02 times 10 raised to the 23rd power. So 1 mole, this unit mole, like dozen, refers to that number of pieces. So 1 mole is this many pieces, particles. So if I had 1 mole of eggs, we're talking about 6.02 times 10 to the 23rd eggs. Okay, so let's go ahead and continue now. We're going to use Avogadro's number to figure out the number of moles that you have in a specific sample. Okay, so if I have a certain number of particles, I may want to know, well, in a large scale, in the mole scale that we actually use on an everyday basis, how many moles do I have? So we can say, for example, if I gave you 12.02 times 10 to the 23rd atoms. Okay, if I give you 12.04, we'll make it clean. 12.04 times 10 to the 23rd atoms is equal to how many moles? Now, all we have to do is think about the fact that, well, I want to go from atoms into moles, so we can set up a conversion factor. Okay, our conversion factor is that 1 mole is equivalent, so I can write it as a fraction. 1 mole is equivalent to my 6.02 times 10 to the 23rd atoms in this case. Okay, any representative tiny particle. So 1 mole of specific atoms are equal to 6.02 times 10 to the 23rd of those atoms. So all I have to do here is set it up as 12.04 times 10 to the 23rd atoms and then I'm going to multiply by the conversion factor. Since I have atoms at the top, I'm going to want to cancel atoms, so that value goes on bottom the way that we have it here. 6.02 times 10 to the 23rd atoms in 1 mole of that substance. When we do the math, you're going to take the top number and multiply across the top and then divide the bottom, and you see that 12.04 times 10 to the 23rd is exactly twice 6.02, so there must be 2 moles. Now, what is very important is that you understand the notation that we use to describe these things. So there are some abbreviations that we can use when we talk about a mole of a substance. We typically abbreviate that by dropping the E and just going MOL indicates the number of moles. Okay. When we think about other units like grams, for instance, the gram is represented by lowercase g. The liter is abbreviated as a capital L. Okay, so it's going to be very important that you're familiar with the abbreviations. However, more important than abbreviations is the order that you write your sample notation. So this is our order. You have to give the amount, the unit, and the substance. Amount, unit, substance. So what we're going to say is if I have 250 grams of lithium, so 250 grams of lithium. Okay. Now the reality here, this is a compound, so these are lithium atoms. Okay. But the way that we would write this is we would say there are 250 grams, so quantity, unit, and then we're going to give the symbol of lithium Li. So 250 grams lithium. Alright, I'll give you a sec to pause, and then we're going to go ahead with these practice problems. I'll assume you've taken that time now. A mole is based upon the number of atoms found in exactly blank of the isotope blank. So, it is the number of atoms found in exactly 12 grams of the isotope carbon 12. So carbon with a mass of 12, it has exactly 6 protons, 6 neutrons. That's where that comes from. Now find the number of moles in each sample. So you're given 3.5 times 10 raised to the 24th power in atoms. So what we're going to do, actually here, I'll do my calculations on here. Kind of helps you to see the specifics. So we want to know 3.5 times 10 to the 24. So 3.5 E24 is the notation. So 3.5 times 10 to the 24th atoms. When I set that problem up, I want to know how many moles there are. So the conversion factor that we're going to use is atoms on bottom, and we're going to take 6.02 times 10 to the 23rd atoms per 1 mole. So to do our calculation, what I'm going to do is I'm going to take that 3.5 times 10 to the 24, and I want to multiply that by 1 on the top, which is just going to be 1, and then divide by the 6.02 times 10 to the 23rd. So I'll take that number and divide 6.02 times 10 to the 23rd power. So if you have this written out graphically, 3.5 times 10 to the 24 over 6.02 times 10 to the 23, and that equals 5.81 moles. Okay, so our answer here is 5.81 moles. Now we're going to do the same process with the rest of these. Notice we've got atoms. Now let's do the same for molecules. Molecules are another representative particle, so it works the same exact way. In 1 mole, you have 6.02 times 10 to the 23rd molecules. So now, we'll go ahead and plug that in. 2.57 times 10 to the 21st power. And then our conversion factor is going to be set up exactly like we did before with the 6.02 on the bottom. So we're going to divide 6.02 times 10 to the 23rd. That gives us 0.004269. So 0.00427 rounded to 3 sig figs molecules. We'll do the same with our 7.447. Divide that by my times 10 raised to the 23rd here, divided by 6.02 times 10 to the 23rd. 1.237. So we want that to 4 sig figs. It'll be 1.237 moles. Oh, sorry, this was moles. And now 1.0 times 10 to the 27. We'll do the math on that. 1.00 times 10 to the 27th divided by 6.02 times 10 to the 23rd. And we get 1661. But to 3 sig figs, that'll be 1660. Okay. So that would be 1660 rounded moles. All right, now a little more practice on that. The table below, this time we're going to go from moles into particles and particles back into moles. What you're going to have to pay special attention to, though, is what kind of particle are you looking at? So if you see moles of Li, you know that Li, we're talking about lithium atoms. So we'll take our 4.57 moles of Li. This time around, we have to switch our conversion factor. We're going to have to take the moles, and to cancel moles, you must have the 1 mole of lithium on the bottom in 6.02 times 10 to the 23rd molecules, or in this case, atoms of lithium. So we'll do the math on that now. And it was 4.57. Let's clear that first. 4.57. Now these are moles, so we're going to multiply the top number this time. We're going to multiply by, so that is times 6.02 times 10 to the 23rd. And then you would divide out the 1, but we don't need to do that math because it will be the same number. And we find that is 2.75. 2.75 times 10 to a whole lot. Let's see. We've got 3, 6, 9, 12, 15, 18, 21, 24. 2.75 times 10 to the 24. Pretty big number. So that will be 2.75 times 10 to the 24. And then, again, remember, what kind of particles do we have? These are atoms of my lithium. Okay. Next, 4.55 times 10 to the 25 molecules of CO2. So this time around, we're going to work backwards. We're going to start with the 4.55 molecules, 4.55 times 10 to the 25th molecules, and our setup has to have molecules on the bottom. So instead of our 6.02 to 1, it's going to be 1 mole of CO2 over 6.02 times 10 to the 23rd molecules. When we do the math, same exact process. But this time around, we're looking at 4.55 times 10 to the 25. 4.55 E25. And because we're starting with molecules, the 6.02 times 10 to the 23rd is going to be on the bottom. So we divide by 6.02 times 10 to the 23rd. That gives us 75.58. And with 3 sig figs, that will be 75.6. So 75.6 moles of CO2. Okay, next up, we have 0.00500 moles of Cu2+. So we have to identify that it's not a compound. You don't have multiple things, so it won't be called a molecule. It's not an atom either, though, because it has charge. These are ions of copper. So we want to use the same setup that we did before. This time I have moles on bottom, so we're going to use that conversion. We are going to calculate it out. 0.005. Since we're starting with moles, we're going to multiply by Avogadro's number, so times 6.02 times 10 to the 23rd, giving us 369. That is 3.01 times 10 to the, let's see, I think it's 21. Yeah, 3, 6, 9, 12, 15, 18, 20 to the 20. Okay, so 3.01 times 10 to the 20. And recall that these are ions of my copper 2+. Now I have moles of F2. So F2, since there's more than one atom together, they're not atoms, they're not ions. This would be molecules we're talking about. We're going to use the same conversion that we did before, the 6.02 on top. So we do the math as 3.5 times 10 to the 4th. And we want to multiply by Avogadro's number again. So that would be our 6.02 times 10 to the 23rd. And that gives us, let's see, 3, 6, 9, 12, 15, 18, 21, 23, no, 24. Wow, my brain's working right now. And what is that, 25? So 2.11, or 2.1 times 10 to the 25. And these are molecules of F2. Lastly, we have 1.5 times 10 to the 23rd molecules. So this time around, we're going to be having molecules on the bottom so they can cancel. So we're dividing by Avogadro's number now. So we'll divide, take our 1.5 times 10 raised to the 23rd power, divide that by 6.02 times 10 to the 23rd power, and we get 0.249. 0.249 moles of Al2O3. So sorry this one ran a little bit long, but this is where things get a little bit more involved, and I just want to make sure that you have full examples for how these work.